Okay, we will move to the improvement of the Euler method. That's for this course. We will mention just only two ideas. That is the first. We will call the HEUN'S method. And the second one, it is a midpoint. Okay. So according to the Euler method, you will see that it is the general concept to approximate the next value of y from the initial value that we already know. Okay, we predict the next value from the initial slope. Okay, and you see that it's maybe easy to understand, but it's not good enough for predict the next value. Okay, so then we may improve the Euler method. Okay, so let's take a look. Let's take a look. The first idea, that is the HEUN'S method. From the HEUN'S method, we know that from the Euler, we predict the next value of y by using the initial slope. So for the Euler, we have this, right? Okay, we predict the next value of y by the initial slope. Okay, multiply with the step. Okay, this is the increment. Okay, that is to be add to the initial value, and it's become the next one. So this is just the Euler. So if we use Euler method, this should be the solution already. After we substitute the initial slope, okay, we use the initial slope to predict the next value. That is enough for the Euler. But we know that the Euler gives us not correct solution. So the HEUN'S method will adjust the slope. That is not used. It is not used just only the initial slope. Okay. So what does it mean? It means that it used the Euler method to predict the value of y at the endpoint. But we know that this value is not correct one. Okay. So then we should adjust or correct the solution again by using this value as the final point. And now we have the value of x at the endpoint and value of y at the endpoint already from the predictor, that is from the Euler. Okay, so then when we substitute the value of x and y at the endpoint into the function, so then we get the slope, we get the another slope, that is the slope at the endpoint. So now we have two slopes that are the slope at the initial point. We call the initial slope. Okay, and we have the second one is the end slope because it is the slope at the end point. So for the idea of HEUN'S method, is apply the initial slope and end slope, and after that we determine the average one that we will call the average slope. Okay, this is just the idea for the HEUN'S method. So now based on the Euler method. Okay, based on the Euler method. For the Euler method, we use just only initial slope. Okay, we use this this is the initial condition. Okay, we know the solution. And after that, we use the initial slope here. This is the initial slope. So that means after we use this value for the initial slope, okay, we will get the solution here. Okay, that if we apply the Euler method, should be the solution. Okay, this point is become the solution. This point, okay, this point is become the solution if we use Euler. Okay, but actually we will not use the Euler. Okay, we know that the Euler will give us not correct solution. Okay, so we will adjust it by using this point. Substitute this point. That is, we already know y at this point, and x. Substitute it back into f of y. That is, we know that it is equal to slope according to the form of equation. That is dy by dx equal to f of y. So then it means f of y is the slope of the function of y. So from this value, we can determine for the slope at the endpoint. That is from the orange line. This is the slope at the endpoint. And the red line is the slope at the initial point. Okay, so then we can determine the average slope right now. Okay, we can determine the average slope here. After that, okay, after we have the initial slope, then we can determine for the average slope. Okay, so after that, we will use the average slope instead in order to determine yi plus 1. Okay, that is the basic idea of one method. Let's take a look at this example. That is the same example. We have this equation. Okay, so then f of y is equal to y cosine x. Okay, so we have the initial value that is y at x equal to 0 is equal to 1, and we will use the step side of 1. So we're starting with the predictor equation. That is actually it is the Euler. If we use Euler method, this is just to be the solution. But for HEUN, it is not the solution right now. It depends on the repeating iterative that we set up. Okay, but for this case, we just do only one times. Okay, and for this case, this is actually it is the Euler. Okay, and it's become just only the predictor for the HEUN method. Right now we have y1, that is when x is equal to 1. Okay, we have y equal to 2 right now. It's from this method, that is a HEUN. Okay, if we use Euler, this is the solution. The solution become 2. But now it is not the Euler. Okay, and we have y1 is equal to 2. We use y1 and x1. Okay, y1 now we already determined it is equal to 2. x1 according to the step, that is s equal to 1. Okay, and x is start from 0. So then we have the end slope equal to 2 cosine 1. It's become this value. Okay, you're right. After that, after we find the slope already, okay, we will determine the average slope from the initial slope and the final slope. After that, we can predict for the value of y from this formula. From this formula, after we substitute each value into this formula, we obtain this. In combination with the exact solution, we will find that the true error is reduced to 0.279. This is the true error, but it is not the percent error. Okay, because this is just only the relative error, that is the difference between the exact solution and another topic. Okay, that's we are self-study for that case. Okay, from this, if we compare the solution from HEUN'S method with the Euler method, you see that HEUN'S method is maybe close to the exact solution than the Euler method. Okay. But it is maybe not good enough. This is just the idea of HEUN'S method. Okay. We may do another example by using HEUN'S method to solve this equation. So from this equation, you see that we can write in this equation is right in the form of dy by dx equal to f(x,y). That is actually this is equal to dy by dx equal to 4e power 0.8x minus 0.5y. Okay, this is f(x,y). You're right. And we have the initial condition that when x equal to 0, y equal to 2. And we would like to find the value of y at any point from x equal to 0 to x equal to 4 with step size of 1. Okay. So according to this equation, we can derive for the exact solution. That is actually this is an example from the textbook. I will not derive the exact solution. Okay. So from this case, we know that from this equation, we have the exact solution like here. That is, you will see exact solution is right in analytical form, and it has the formula of y. Okay. And after that, we can create a table. Okay. We set up value of x, and we create a table to determine the exact solution here according to the position of x here. Okay. And after that, we apply HEUN'S method to solve this differential equation. And we found out when we apply HEUN'S method with the initial condition, that is when x equal to 0, y is equal to 2, that is the initial condition. We substitute x equal to 0 and y equal to 2 into the equation. We obtain y1 is become 5. Okay. After that, we use y1 that is become 5 and x1 also. Okay. We substitute x1 and y1 into the function f(x,y). Okay. Now we have the end slope. That is over here. After that, we determine the average slope. And we obtain the average slope here. Okay. After we have the average slope, we can use the average slope to predict the correct value of y at next step. Okay, this is determined from the initial value, and this is the average slope, and this is the step size. After that, we obtain this value. This all for the HEUN'S method. Okay, and we will working with the HEUN'S method by we may set up the table like this. Okay, you see that set up the table. That is mean that we will determine the initial slope, that is fxy. And after that, we determine the predictor. Predictor is the y from the Euler method. And after that, we use this value of y. We use this value. Okay. We use this value to determine the end slope. Determine the end slope. And after that, we have the initial slope and end slope. We can determine the average slope. And after we have the average slope, we use it to approximate the next step of the value of y. Okay. For the first step, you see that we determine the initial slope. Okay. And the predictor, that is the value of y at x equal to 1. We have this value. After that, we use this value, okay, for we use this value for determine the we use this value to determine the end slope here. We use this value determine the end slope. We use this value determine this value end slope. Okay. And after that, after we get end slope, we will use the end slope and initial slope to determine the average one, which we obtain here. After that, okay, we use the average slope multiplied with h, okay, adding into the initial value, okay, we obtain the solution for y, for the next step of y. Okay, you're right. And after that, we can repeat for another step. And we have to believe that this should be the correct one, but actually it is not. Okay, it is just predict from the initial value. So we know that from the Euler, this value is normally it is not the correct one. We have to adjust a lot. But for this case, just only the concept. We have to believe that this value it should be all right, and it's become the next initial value for next step. Okay, I recommend you to do this example again by yourself without the solution. You may recalculate each value in this table by yourself. Okay. So according to this, we found out when we determine for all steps, repeat the procedure, we have this value. And after that, when we compare with the exact solution, we will see that for one method with just only step size of 1, we have the value in comparison with the exact solution is maybe not good enough, but it's better than the Euler method. As we mentioned before, for the HEUN'S method, we see that we may repeat it again after we correct the value. Okay. For HEUN'S method, it's just only one iterative. We will have the solution of here if we compare the previous slide. But for the case of HEUN'S with iterative, so what does it mean? It means that we know that this is maybe not correct one. So then we will determine the slope again. We will determine the end slope again. And after that, we determine the average slope again and correct it again. Okay, we do it again and again. Until what? Until the value of y that is very close to each other at the final step. That is give us the envelope become the same value. Okay. And also, after we have the envelope at the same value, we will have the average slope become the same value also. It means that y at next step, next iteration, it should be enough. It should be close to the correct value. That is, we cannot do this is just should be the better one. Okay, for the Huon method, something like this. Okay. And it is the limitation for the Huon. Although we do a lot of iteration inside of the Huon, so it maybe not give us more than this. It's maybe the solution is maybe not better than this, and we have to we do it better for the Huon method, something like this with the Huon with more than one iterate, with more than one time. Okay, we repeat it again and again. For this case, we repeat it just 15 iterative for each value of step size. We do 15 iterative. Okay, understand? For another step, we do it again. Okay, and we repeat it 15 iterative. That is we obtain here. But I do not would like you to mention this slide a lot, because it just give us just only the idea of the Huon method, and it is not good enough. This table from the text show us that if we use Huon method with step size of 1, with step size of 1, that is actually is not good enough. Okay, it gives us the error of the in comparison with the exact solution, it may be reduced. Okay, it may be reduced, but it's still in the range of 8 to 10% for just only one iterative. But if we do 15 iterative, the error is reduced from 8 to 10%, become just in range of 3%. But actually, I think for this case, it's maybe not good enough. Okay, but we can reduce the error by reduce the step size also. If we use the small step size, it may give us the better solution. Okay, and now we will move to the final one, that is the modify Euler. The concept is same as the Huon method. We know that from the Huon method, we know that the Euler, we use the initial slope to predict the end slope, and after that we use the end slope. Okay, we determine the end slope and approximate the next step value by using the average slope instead of just only initial slope. Okay. From this idea, similar to the Huon method, okay, the modified Euler method or the midpoint method, we will not use the end slope. We use the slope at mid step instead. So that means that we have the initial value here. Okay, if we use the Euler, what does it mean? If we use the Euler, so we will get, if we use the Euler, we will get the solution here. The solution should be at this point. If we use the Euler, and if we use Huon, we will determine the end slope. Okay, and after that, we will use the average slope to predict the value of y in next step. But for the idea of midpoint or modified Euler, we will not use the endpoint. We will use the Euler just only mid-step. Okay, so it means that we use the Euler just only mid-step. We will choose it just only a half step side. Okay, and after that, we get this point. Okay, and substitute this point, substitute this value of y and x into function f x y. We will get the midpoint slope. Now we get the midpoint slope here. Get slope at midpoint. And we will use slope at midpoint to predict the next step instead. Okay, this is we call the modified Euler method. So for this idea, okay, so the step is we use the Euler, okay, to predict the value of y at mid-step. And after that, we use the value of y at mid-step, determine the midpoint slope, okay, mid-step slope. And after that, we use the mid-step slope to predict the endpoint instead. This is the idea of modified Euler. Okay, we do the same with the same example, and we obtain that the error from the modified Euler is it's about 0.00341. This is the error, it's not the percent error. So actually it's not good enough. It's just the error is about the third decimal. This is not the percent error. Okay. So and it is accidentally for the midpoint method that is maybe the best one for this case, but actually is the error obtained from the modified Euler and HEUN'S is maybe it should be the same order of the error. Okay, and if we compare with the solution, if we use Euler, HEUN'S and modified Euler with the exact solution, we will see that for HEUN'S and modified Euler or the midpoint method, okay, the error is maybe this two method is better than the Euler, okay, but it's still not good enough. Okay, and according to this idea of these three methods, we will expand this concept to be the next one, that is we will call the Runge-Kutta method. That is based on this concept, which changing the increment function to be the spatial function. That is very good function to adjust. Okay, so because when we compare with the Euler method that we study today, we know that yi plus 1 equal to yi plus f xi yi, that is the initial slope times h. This is the Euler, right? And after that, for HEUN'S and modified Euler, it just change this function, okay, for HEUN'S, okay. For HEUN'S, is use the average slope. It just only change this, okay. And for midpoint, okay, its change is to be the slope at mid-step, right? Okay, so the key idea of this technique is to change this function, right, to be the better one. Okay, therefore next method, that is the Lunge-Penta method, we will define this as the function phi, that is the increment function. Okay, thus we will use the same technique but with a little bit adjust. Okay, we will increase the term to adjust the increment function to be the special function, that is make the solution very close to the exact solution. Okay, we will mention to this again next time. Okay, so that it should be enough for today.